Video here on inverses 5.2. I'm going to go a little speedy since you can pause and rewind. Inverses is our 5.2. Okay, so we're going to find the inverse, which is noted by f to the negative 1 of x algebraically. All right, so if you recall, the steps to doing this are to replace f of x with y. There's step 1. Interchange x and y, therefore you, right here, you technically have your inverse, but we do want to solve it out for y, so we can write it with this notation. All right, so this will be x minus 2 equals 2y, and let's just flip that around so it looks more traditional. Divide by 2 everywhere, and just so it looks like a line, I'm going to actually split that 2 to being 1/2 x, because that would be x over 2 and then minus 1. 2 over 2 is 1. So that looks, more like a y equals mx plus b form. So f inverse then is 1/2 x minus 1. So to summarize those steps in this box here, we replace function notation with y, interchange x and y, solve for y, so isolate y on one side, and then replace y with the inverse notation. Okay, perfect. If we were to graph these, so if we were to graph f of x equals 2x plus 2, I would go to 0, 2 here, and then go up 2 over 1. So that would be at 1, 1, 2, 3, 4. Okay, and there's that line. Just grab another point, go down to. All right. And then I'm going to change pen colors here, and let's graph our inverse. So our inverse is at negative 1 for a y-intercept, negative 1, and then up 1 over 2. So that's 2, 0. Okay, and so we'll complete this line. All right, so we'll just go get another point here. All right, so there is f inverse, and here is f of x. Okay, so an important point here to note is going to be 0, 2, and 2, 0. Notice how they flip-flopped. But the 0, you can't really much tell that it flip-flopped. So let's look at 1, 4 on the original and see what happens in the inverse at 4. Notice if I put 4 in here, I get 1/2 times 4 minus 1, which is 2 minus 1, which is 1. So you actually get 1, 2, 3, 4, 1 on this graph. 4, 1. And so you can see between these 2 points, look what happened. Well, when you interchange x and y on this step, right, we interchanged x and y on this step, that means the points will also interchange on the graphs, okay? So let's write some properties here. Functions and their inverses are symmetrical over that interchange. Okay, so if you put the line y equal to x on here, which is just your identity line, I'll try to change to a little purple here. That's just going to go straight up through this diagonal. You can see that the inverses make a reflection over that line, and that's because of that interchange of x and y. They are perfectly reflected over that line. If you were to fold over that line, the lines would be on top of each other. If f of x contains ab, then f inverse will contain BA. That's your interchange here, like we saw right there. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. And then again, that's because domain is x, range is y, and when those flip-flop, as do the domain and range. Okay, so there's an important property for inverses when you take a composition, which was 5.1, in both directions, it will equal x. And this is how we prove or show that they're inverses. This is the property of inverses. So demonstrate this property, and you'll have to do this on a test. So know this system here. So this is called the identity for functions. And so to have an inverse, you want to get to that identity. Just like 3 and negative 3 are inverses in addition, they get us to negative 3 and negative 3 get us to 0, which is the identity for addition. And 3 times 1 over 3 get us to 1, which is the identity for multiplication. Well, x is the identity for f of x, because when you plug in x, you get the function itself. Okay, f of x, plug in x to f of x, and you get the function itself. So that's why we're trying to get to x here, to show that there's no they produce the same thing, the identity, and that means they are indeed inverses, just like 3 and negative 3. Okay, so demonstrate this property for the above. So I'm just going to plug, let's go f of f inverse. So let's plug that inverse into f of x at x. And so this would be, the inverse is right here, this 1/2 x minus 1. So we've got 2, 1/2 x minus 1, and then plus that 2. All right, so this is x minus 2 plus 2, which is indeed x. Check, and you have to do this both directions. So now I'm going to take 1/2 and plug in 2x plus 2, and this minus 1 is right there. So that is x plus 1 minus 1, which is x. Check, check. Property of inverses. Okay, so we're going to do it with a more complicated one. Some baby fraction work will come in here, I think. Use when your directions on the test say to use the property of inverses, this is what you want to do. Plug them into each other. All right, so this is to put f of x into g. So this is going to equal negative 3 minus 5, parentheses. That's where we want to put f of x. I'm just writing g down and leaving a big parentheses here for f of x. Okay? So now let's put in that f of x, negative 3, 2x plus 5, negative 3, 2x plus 5. All right. So let's get rid of, well, I don't know. Let's see, what do we want to do here? Let's maybe do negative 3, and let's get this going. This will be plus 15 over, this might look a little more simple, 2x plus 5, and then this will just be negative 6 over 2x plus 5. Okay, so let's multiply by 2x plus 5 over 2x plus 5. So this whole thing will distribute here and here, and then just to that negative 6. Running out of room. Okay, so up top I'm going to go ahead and multiply that out because I'm out of room. Negative 6x minus 15 plus 15. Okay, so this will go to this numerator, but this here, once that goes to that negative 3, it resets, it goes to both, it's distributed both, that's going to cancel that out. And then you just got that plus 15. On the bottom, it'll just straight cancel here. All right, and we've got this negative 6. So you can see where this is heading. Negative 6x over negative 6 is certainly x. So that is verified on the left. All right, so same thing on the right. Let me move myself up here so you can see that one while I'm looking. Okay, so now we're going to plug g into f. So here's f. And I'm just going to leave a big parenthesis here. Okay, and so that'll just kind of help me get my plug in correctly. And then I'm going to plug in this g here. So negative 3 minus 5x over 2x. All right, so let's clean it up. Negative 3 on the top. This 2 will go in here. So we'll get negative 6 minus 10x over 2x, and then this is just plus 5. All right, so 2x and 2x. So this top will be negative 6x. This will distribute here. Knock it out over there. This will just be negative 6 minus 10x. And then this resets and also goes here for plus 10x. And looking good, This is negative 6x over negative 6, which is x, totally verified. Okay, they are indeed inverses. So I'll let you look at that for a second. Okay, my hands may have been away a little bit. All right, so let me look at some more notes here. All right. You can always pause and rewind, so I'm going to go ahead and flip. All right, so more on the graph of inverses. Sketch the graph of the inverse and determine if the inverse is a function. So to be a function, we have to pass the vertical line test. The vertical line test determines if a relation is a function or not. Okay, so I'm going to graph in this identity line. And the easiest thing to do, instead of just trying to sketch it, is to grab these points. That point is 0, 1, so I'm going to plot 1, 0. That point is 1, 2, so I'm going to plot 2, 1. And this point is negative 1, 1, so I'm going to plot 1, negative 1. 0, 1, 1, 0, negative 1, and negative 1. Oh, gosh, that's a half. Sorry. So I'm going to go negative 1 and a half. All right. All right, so that negative a half 1 will become, this negative 1, negative 1 a half, there we go, will become 1 half and negative 1. So right about there is that one being flipped. 1 half, I think I misspoke earlier. 1 half, negative 1. Okay, so just labeled 1 to kind of get us in check there. You can see this is running along the x, so this is going to run along the y. Look something like that. Okay, so see if this is a function. The inverse, which is in red, this is f inverse, if it's a function, and just do this vertical line test, and indeed it is a function, it passes. Okay, oops, you can't really see that, there we go. So the next one we're going to do the same thing. I'm just going to flip these points around. That's 1, 1, so I'm going to go negative 1, negative 1. That's negative 1, 1, so I'm going to go 1, negative 1. All right, so this is 1, 2, 1, 2, 3, 4. So I'm going to go 1, 2, 3, 4, 2. Okay, and this is 0, 0. So this is 1, 2, 1, 2, 1, 2, 3, 4. So negative 2. So I'm going to go 1, 2, 3, 4, right there. Okay, so this one of these points is wrong here. What's wrong here? 1, 1. This is 1, 1 is still 1, 1. All right, so that's still this here. And then negative 1, 1 is going to be 1, negative 1 here. And this point is out of place. Sorry about that. I'm at lunch on Thursday trying to hurry through this video. So anyway, there they are flipped. There's 4, 2. That's 2, 4. There's negative 2, 4. So that's this one up here, I guess. That's 2, 4. So this is 4, 2. This one is negative 2, 4. So this is 4, negative 2. I think that's enough here. 0, 0 just flips, so we get this graph. All right. Fumbled around that one. Okay, and so boom, fails vertical line test. No. All right, so there's a quick way, instead of going through all of that, and you can see that it is symmetrical about this line. Okay, y equal to x, 12:47. I got 5 minutes. Okay, I may have to pause this. So there's a quick test that'll tell you how you know if a function has an inverse that's also a function. So here's one that worked, right? So this passed the VLT, of course. If it's a function, it passes the VLT. If it also passes the HLT, well, those horizontal lines, when x and y switch, will become the vertical lines here. So these horizontal lines on the original become these verticals here. So if the original function will pass the horizontal line test, the inverse will be a function. So you don't even have to go through the rigmarole of graphing this and graphing this. You can just look at the original and say, pass VLT as it should if it's a function, also passed HLT, which means the inverse will pass the VLT with that x and y interchange. Right here, this certainly passes VLT, great, but fails the HLT, which means that horizontal line will become these vertical lines when they switch on the inverse, and that means the inverse will not be a function. So in short, we use the VLT to determine if the relation is a function or not, and then the HLT to determine if the inverse. Okay, so the function here is not a function, fails the VLT. The inverse of the relation, since it's not a function, does pass. All right? And then here, this is a pass. So that is a function, yes. And right here, I find a place right here where we fail. We're failing the HLT, so no. Okay, this one fails VLT, and this is a fail of HLT. So notice we're not even looking at the inverse of the function. We're only looking at the original. Okay, and this is a, wow, failing VLT, failing. This is not a function, and nor is its inverse. Okay, so that's a really nice way to test that. So definition here, this is the definition. A function is one-to-one, and then I'll stop and pick this up after school, I think. It's 12:49 in here. A function is one-to-one if and only if, that means if and only if, the inverse is also a function. This means each input has exactly one output from exactly, that came out of exactly, and each, oh sorry, let's say that came from right there. So this means that each input has exactly one output, and each output has exactly one input, so it goes both ways. Okay, so each output came from exactly one input. So basically how I talk about it, now 92 going to an A and 95 going to an A is not going to be okay, because when you flip those, you're going to have divergence, okay? So this is what we call a one-to-one correspondence, all right? So this is graphically a one-to-one function, one-to-one. It must pass, the VLT and the HLT. That's a one-to-one, I like that, one-to-one correspondence of points. One-to-one function. Every x goes to only y, and every y only came for one x. Okay, and so this is where we put in another little thing. If f of a equals f of b, okay, so like here, if you've got two y values are the same, a and a, then that a and the b had to be the same, meaning 92 had to equal 92 if we're going to get an a and an a here. All right, I mean, it's not really makes sense with grades, but that's the analogy that we keep using. All right, so I'm going to pause. Hopefully this doesn't kick me out. If so, I'll just do two little videos, but we got to do another page and a half. Another page and a half. All right, see you guys in a little while. Okay, going to finish this out. Kids just left. Testing for a one-to-one function is the next little piece here. We have a and b, and they're non-negative real numbers, such that f of a equals f of b. So remember, before it said then a has got to equal b. So the first thing we're going to do is sketch this, and we'll get here, and when we put 1 in there, we'll just be at 2. When we put 2 in there, we'll be up at 5. So let's just do that to give myself some room. Okay, so like that. So we've got 0, 1, and then 2, 5, and then negative 2, 5. So we're testing to see if it's a one-to-one function. Okay, so if you see where f of a equals f of b, so 5 equals 5. However, a, for whichever one you want to be a, 2 does not equal negative 2, okay? So f equals, the y values equal, the x values don't, so we say that this is not the same. So this means this is not one-to-one. So f does not have an inverse. That's a function. Okay? So there's that one. So the next part of this is going to be over here where we graph this one, you can also see that this passes VLT. There's another way graphically is that it passes VLT and fails HLT. All right. So this is, give an example of where f of a equals f of b, but a doesn't equal b right there. We had 5 equals 5, but 2 did not equal -2. Okay, so that's already been done. All right, so let's graph this square root shifted right one. So this will be at 1, 0. And then our square root function, which let's go over to 4. Or actually, let's even go over maybe to, we'll go to 4. So when x is 4, we get 1. Okay, so we put 4 in there. We get root 4, which is 2, minus 1, which is 1. So we get a graph that looks something like this. Okay? And then, see, we didn't have to graph this one since it didn't exist. So we need to, look at something here that is on level. And so let's find a point, the two y values that are the same. Whoops. So let me find a y value that, we can use for that. And this one we're going to have to do a little bit more theoretically. So this one we can actually see those points. This one we're going to have to put in some f of a equaling root a minus 1. And then we're going to have to put in some other, this f of b. We're just going to have to actually, figure out what these are, since we don't have other parts to this square root graph. We can't just see it. So we're going to do f of b minus 1. Okay? And so what we're going to do is just simply set these two equal to each other. Okay? So if f of a equals f of b, then this should work out. So we're going to set f of a equal to f of b. So if root a minus 1 equals root b minus 1, let's see if this holds here. We can add, basically cross those out, and root a equals root b. This is kind of like a geometry proof, if you will. Can we make this work so that they end up being equal? And we can. So those are equal. That means this f here is 1-to-1, and f does have an inverse. Okay, so that's just kind of like we couldn't get any points to look at, so we had to do kind of like a proof. If f of a is this, if f of b is this, if we set those equal, when it all shakes out, can we prove that a is equal to b? And so, yes, we can on that one. All right, last page over here. How can we guarantee that we can find an inverse? Okay, and they wanted us to graph this inverse, so let's graph the inverse. So this is 4, 1, so now I want to graph 1, 1, 2, 3, 4. Okay, and then this is 1, 0, I want to do 0, 1. And this is 1, 4. So this one would just graph, like so. And you can see that symmetry over this line. Okay, so let's go to the next page. So how can we guarantee that every function, or a function has an inverse? So this one did not have an inverse, okay? Because it's not 1-to-1. We showed it algebraically and with the horizontal line test. Or actually, we just showed it with points. 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's just go here and say 2, 5. And then right over here, -2, 5. Okay, so what we can do is do something here where we look at the domain and range, always here, and the range is then -1 and up. 1, hello, 1 and up. At least I catch on this edge, right? Okay, so 0, 1 there. Okay, so we are going to, is the inverse a function? No. How do we know f of x, or g of x, the original, fails the HLT? So what we're going to do is restrict the domain. We're going to write a rule, find a rule for the inverse for the given function. If the inverse is not a function, can you restrict the domain so that it is a function, and therefore 1-to-1? meaning every x will correspond to exactly one y, and every y will come from exactly one x. So, you know, where could we just pick up a piece of this that's one-to-one? And so we could just start here. If we just got rid of the duplicates on the negative side, we could just pick this part and write a function rule that will just graph this, and therefore we could make this have a function with a restricted domain. And so if we restricted the domain, we would just go here and say, hey, let's restrict the domain of g of x and make it a function. And so we would just say 0 to infinity. Technically, you could restrict the negative side too if you were feeling, you know, like you wanted to go negatives, but usually we just go with the positives there. All right. So sketch these on the same axis then. So this one now would just be in the blue. This would be 0, 1, so I do 1, 0, and 5, 2. 1, 2, 3, 4, 5, 1, 2. And so the inverse on the restricted domain would look like this. So this would be g of x, and then this would be g negative 1 x. Well, this we just we throw that away. We're just going to throw that away. Throw this away. Restrict the domain. So we're only looking at the right side. So this is g of x with this restricted domain. And therefore it has this inverse here. All right? Okay. So let's see what else we have to do here. Sketch the inverse on the line. We did that. And we've got a line of symmetry here. That's y equal to x. Okay. Did that. Okay. Sketch the inverse on the same axis. We did that. Okay. And let's talk about the domain and range of the inverse. Well, let's go back to here and look at, we're going to restrict this domain to 0, infinity. Okay. And then look at the range here. Okay, so let's analyze the domain and range here now. So g inverse of x is now starting at 1 inclusive and going to infinity. Okay, so this is 1 inclusive going to infinity. And the range, the lowest value of y is 0, and it goes on to infinity. So this is 0 to infinity. Notice from here, this restricted domain became here, this restricted domain became the range here. This range became the inverse's domain. So the domain of the original became the range of the inverse, and the range of the original became the domain of the inverse. Okay? Domain and range. Switch. Which makes sense, because how do we get an inverse? We switch x and y, and domain is x and range is y. All right, so conclusion. Let's just do a bunch of little bullet points here. If a function, if it says it's a function, it passed VLT, so that's assumed. If a function passes the horizontal line test, we know it is 1-to-1. Visually, a 1-to-1 function must be strictly increasing or strictly decreasing. Okay, often it's possible to restrict, often, not always, it's possible to restrict the domain of the original function so that we can find an inverse if the original function did not pass the HLT. Oh, sorry, we want to pass both the VLT and HLT. Okay, remember a function and its inverse have special relationships, symmetric over the line y equal to x. That means if AB is a point on F, then BA will lie on inverse F. Okay, the domain and range switch. Between a function and its inverse, and if you compose them either direction, the result should be x. All right, that's it for the video. So I'll see you guys back in class in a couple days. Okay, take care. Bye.